everyone. So today we are doing lesson 4.3, which is sums of arithmetic series. It is going to be an extension of what we learned in 4.2. So first, what I'd like you to do is a warm-up exercise. I want you to write the explicit formula for the arithmetic sequence that has the terms a sub 4 is 22 and a sub 8 is 46. And once you have that explicit formula, I want you to find the 25th term of the sequence. So pause the video now and let's make sure you're comfortable with this first problem before we move on. Welcome back. Let's see how you did. So first, since I know I'm dealing with an arithmetic sequence, I know that this sequence is going to behave like a linear function. So if I find, the slope of the line that's passing through the points 422 and 846, I know that that will be my common difference. So I'm just going to use slope formula and know that that's my common difference. I'll have 46 minus 22, the change in the y values, over 8 minus 4, the change in the x values. So when I take 46 minus the 22, I get 24. 8 minus 4 is 4, and therefore my common difference is 6. Now I'm going to decide to use this first a sub 4 term because the numbers are smaller, and I'm going to find the first term. So I'll have 22 equals a sub 1 plus the common difference times the n value minus a 1. I'll write that explicit formula for you here in case you need it to reference. So when we clean this up, we get 22 equals a sub 1 plus, I know this 4 minus 1 is a 3, and 6 times 3 is 18. So I'm going to subtract 18 from both sides, giving me an a sub 1 that is equal to 4. So my explicit notation is a sub n equals 6n, and if I need to know what that 0th term would be, I would take 4 and subtract the 6, so I'd get a minus 2. Or you're always welcome to plug in your a sub 1 here as 4, and your common difference here is 6, and simplify, and once you simplify, you'll see that we have the same explicit formula for the sequence. Remember again that arithmetic sequences behave like linear functions, so this kind of looks like the slope-intercept form for a line. Just bringing that relationship back where the common difference corresponds to the slope, and this number here corresponds to the y-intercept, or the 0th term in the sequence if it existed. So now it says to find the 25th term in the sequence. So to find the 25th term in the sequence, I'm going to find a sub 25 by plugging in 25 for my n. 6 times 25 is 150, and 150 minus 2 is 148. So this sequence would be, let's see, it starts with a 4, then goes up by 6, goes up by 6, dot, 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 dot. I know that the 25th term would be 148. Let's get a few terms before it. If I were to subtract 6 to find the 24th term, I'd be 142. If I were to subtract 6 again, I'd get 136. So here, I can see this right here is the first term, second, third, 23rd, 24th, 25th. And then I could say dot, dot, dot. Because of course it could keep going. I was just looking at the 25th term in the sequence. So now let's look at the next question. It says, what is the sum of the first 25 terms of the sequence? The sum. So when I read sum, I know that means addition. So they're asking me to take the first term, which is 4, and add the second term, which is 10, plus the third term, plus all the terms, 23rd, 24th, and 25th term, and figure out what on earth that equals. So as of right now, I have one option, and that is to pull out my calculator and plug these in and grind this out and find what the sum is, Or you could do it by hand. That would take you even longer. But my instincts tell me there has to be an easier way to do this. There just has to be. So first off, let's define a sequence versus a series, because we're dealing with something different now that I'm adding up the terms. So remember, a sequence is a list of terms and I'm going to put that sometimes follow a pattern. We are really only interested in the ones that do follow a pattern in this class, so that's the ones we're talking about, but a sequence really can be any list of terms. Now a series is the sum of the terms of a sequence. The sum of the terms of a sequence. So every sequence has a corresponding series where you're adding up these terms. Let's do a couple of examples. So here's an example of a sequence. 1, 2, 3, 4, 5. So its corresponding series would be the sum of all of those terms. 1 plus 2 plus 3 plus 4 plus 5, which is 15. Let's look at another one. What if I had 3, and let's add 4. Let's do an arithmetic team, we're adding 4. So 7, 11, 15, ... So you can see this is an arithmetic sequence that's infinite. So your series that corresponds would be 3 plus 7 plus 11 plus 15 plus ... Since this series never ends and every term is 4 greater than the one preceding it, you're always adding a bigger number, my sum is infinite. So the series would be infinite. Let's take a look at one more example with the warm-up one we were just looking at. So in the warm-up, we have the sequence 4, 10, 16, and then terms. Then we have 136, 142, 148. So this is a finite sequence that terminates. The series would be the sum of all these terms. And that's the question we're trying to solve. We know it has a sum because it terminates. The question is, what is it? How can I easily find that sum? So let's do some investigations and review some notation before we get into how we're going to tackle that addition problem. And be thinking about different patterns you see. And if you did the skeleton tower activity, we might have a relationship that we can pull back from that activity if you did that with us in class. So let's review sigma notation. So we learned about sigma notation back when we defined the mean back in chapter 1, but it's definitely been a while. So when you have sigma notation, here we have our rule for our series defined in explicit notation. Here we have the first number we plug in to that rule, and then here above the sigma sign we have the last number we plug in. And remember, you plug in every consecutive integer from the first to the last. You plug in every consecutive integer. So let's take a look at an example. I want to evaluate the series 3n squared plus 5 from n equals 1 to 4. So I know I'm going to be plugging in n equals 1, 2, 3, n equals 3, and n equals 4. And I'm going to be adding up all of these terms because that is what the sigma is telling me to do. So when I plug in n equals 1, I get 3 times 1 squared plus 5. That gives me an 8. Then I plug in a 2, so I'll have 3 times the 2 squared plus a 5. That's a 17. Then I have 3 times 3 squared plus a 5, and that's a 32. And last I have 3 times 4 squared plus 5, and that is a 53. If you wanted to see just one of those, let's plug in the 4. So if I plug in the 4, I would have 3 times 4 squared plus 5, just so you can see I'm plugging the value right into my rule. 4 squared is 16. And 3 times 16 is 48, plus the 5, and that's where I'm getting that 53 from. All right, so finally, all I need to do is add these together to get the sum of my series. So I noticed that 8 and 32 add to become a 40. And then I noticed that 17 and 53 add to become a 70. So I get 40 plus 70, which is 110. So the series from n equals 1 to 4 of 3n squared plus 5 is equal to 110. Okay, so let's consider the previous example. How would I write the series of the sum from n equals 1 to 25, the first 25 terms in the series, in the sigma notation? So first, let's start by drawing my sigma. I know my rule, my a sub n, was 6n minus 2. And I would be starting with 1, because if I plug in the 1, that's how I would get the 4. Then I'd plug in a 2, and that would give me the 10, the 16. And since I'm ending with the 25th term, that would be my end value. So this is equivalent to my series. By plugging in n equals 1 and all the consecutive integers up to 25, I would generate that series. Let's look at this series. 1 plus 2 plus 3 plus 4 plus 5 plus 6. I'm going to write the series in this sigma notation, and that's going to require an explicit rule. So as I'm taking a look at this, I notice it's arithmetic. Every term is going up by 1. But I also notice that a sub n is always just equal to n, the step size. So there's my rule, a sub n equals n, and I'm going from n equals 1 to 6. Now I have a question. Is this the same series as k equals 1 to 6 of k? And j equals 1 to 6 of j, or even I equals 1 to 6 of I? And the answer is yes. In these three that I've drawn, all I've done is I've changed the index letter, but they all mean the same thing. Here, I'm telling you to plug in these integer values for n in my rule. So I've just redefined it for k, j, and I, but they would all generate the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6. So now find the sum of the arithmetic sequence. So if I'm finding the sum from 1 to 6 of n, I'm just adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, and I can just easily do that. I get a 21. It's not bad at all. But what if I extend the series? So I'm going to take the same exact series, but I'm going to extend it out to 150. Now let's write that series in sigma notation. My rule is still n, but now I'm going from 1 to 150. So you can see here are my domain values, my inputs, and my outputs are equal to the inputs. That's why my rule is still a sub n equals n. So I want to find the sum of this arithmetic sequence or series, and I'm hoping maybe this will help me glean some insight into maybe a formula or a pattern. So I told you guys a story whenever we did the skeleton tower activity about a mathematician named Gauss. So let's remember that story. So what Gauss did was he noticed that if I have an arithmetic sequence where I have a common difference from term to term, if I take the first term plus this last term, if I add these two, I get 1 plus 150, and that is 151. Now if I take the second term and the term preceding the last term, on the left-hand side I go up 1, but on the right-hand side I go down 1, so the sum still remains to be 151. Then I could do it again. If I continue to go in and back 1, I can see 3 plus 148 is still 151. And the sum will always be 151 as I creep in to the inner two values, because when I'm adding 1 on one side, I'm subtracting 1 on the other. So when I'm finding the sum, I'm really saying, all right, every single time I pull these together, I get 151. The question is, how many 151s do I have? How many groups of 151? Well, I have 150 terms here, and I'm pairing them off into groups of 2. So how many groups of 2 will I have? If I take 150 and divide that into pairs of 2, there will be 75 total pairs. So I have 151 times 75, and that gives me $11,325. I don't know why I just said dollars there. It's not dollars. It's just $11,325. And I said it again. I know why I said it. Okay, so my students in class, when I taught this the other day, were struggling with why it was 75 pairs, and so I used money as an example. So we had a semi-formal dance recently, and so what I said was, let's pretend like the first 150 students who come in, I'm going to pair them off into couples and give them $151 each. So as they're checking into the dance, just write in order. The first 2 people that come, I'm putting them in a group. The second 2 people who come, I'm putting them in a group. Third 2 people that come, I'm putting them in a group, until 150 total people have walked in the door. And so when we did that, we said, all right, 150 people are in, but how many groups of 2 do I have? And they easily told me 75 groups. So they're picturing the 75 groups, and I said, now picture that I go through each group and I give $151 to each group, so to each couple that has come in. How much money have I distributed to the first 150 people in the dance? And the answer is $11,325. And then we talked about how I do not have that much money to give away, and that won't be happening at the dance. But I think it helped us realize what was going on here when I'm adding up the first and the last term, finding that sum, and then I'm multiplying that by the total number of groups I have. Okay, so that was a fun story. So now, let's talk about finding the sum of a finite arithmetic sequence, which you just did right there. So the first thing is notation, is just recognizing this S sub n. So S sub n stands for the sum of the first n terms of a sequence, of a sequence. So the sum of the first n terms of a sequence, which therefore makes it a series because I'm adding up those terms. And so what we found was we can add the first and the last term if it's arithmetic, and then multiply that by the total number of terms over 2. So let's go back to our original problem because we can solve this now. So consider the series from n equals 1 to 25 of 6n minus a 2. This was from our warm-up, and this is kind of the one we've been working with since the beginning of the lesson. So my first term is 4, my second term is 10, my third term is 16, and then I have my last 3 terms would be 136, 142, and 148. That is my 25th term. So what I'm going to do to find the sum is I'm going to take 4 plus 148, and that's going to give me 152. And then the question is, how many groups of 152 do I have? Notice 10 plus 142 is 152. 16 plus 136 is 152. And I will continue to just get 152s as I pair them off. So I have 152 times, now how many pairs do I have? Well, I have 25 terms. So I have to take 25 and divide that by 2. So I have 152 times 12.5 total terms. So when I multiply this out, I get 1,900. Boy, I'm glad I did not just try and add that up on my own. So this would be like S sub 25, the sum of the first 25 terms of a sequence. So there we go, problem solved. Now let's formalize all of that with some formal notation. So hopefully oops, I didn't mean to do that. Hopefully you've got some space left in your notes. So let's say S sub n is going to be equal to the first term plus the last term, so a sub 1 plus a sub n, times the total number of terms divided by 2. And you see this a variety of ways in different textbooks, so don't get confused if maybe they put this n over 2 first. Multiplication is commutative, so you can do that. I also see this notation really popularly where they say the number of terms times a sub 1 plus a sub 2, or a sub n, all over 2. I see that notation where they're just distributing that 1/2 to the other term, and that's fine. But if you understand where it comes from, then you're always going to be able to find the sum. If you understand that it's always just the first term plus the last term times the total number of terms over 2, you're not going to depend on this formula if you understand the pattern. All right, so let's take a look at some examples to sum up this lesson. So in the first one, I say if a sub n is equal to 5n plus 3, evaluate the series from n equals 1 to 26 of a sub n. So I'm asking to evaluate n equals 1 to 26 of 5n plus 3. So it's important to recognize that this is arithmetic with a common difference of 5. Because it's arithmetic with a common difference, that's what's going to allow me to use my logic that the sum is going to be equal to the total number of terms divided by 2 times the first term plus the last term. Well, the first term, if I plug in a 1, I get an 8. And if I plug in 26, I get 133. So cleaning this up, I get 13 times 141, giving me 1,833. All right, so the next example, I want to evaluate the sum from n equals 4 to 72 of 3n plus 2. So again, I notice this is arithmetic. My common difference is equal to 3, and that's important because that's what's going to allow me to continue using this logic. But I see something that's a little off here. I see this n equals 4. I'm not starting with n equals 1. I'm starting with n equals 4. So let's go ahead and knock out the first term plus the last term because this whole number of terms thing I'm not quite sure about. So the first term, if I were to plug in 4, because that's what it tells me to start with, is going to be a 14. If I were to plug in a 72, I get 3 times 72 plus 2, which is a 218. And once I figure out how many total terms I have, then I'm going to be good to go. So here the issue is, a lot of my students want to say, all right, I just take 72 minus a 4, that is equal to 68, and that is how many terms that I have. A lot of students want to do that, but that is not the case. I always put these examples right on top of each other, 1 and 2, for a reason. Think about up here. When I was taking the sum from n equals 1 to 26, you didn't say 26 minus 1 and there's 25 total terms. You didn't do that. You have 26 total terms. Because if I were to take 26 minus 1, what that would do is that would cancel out the first term as if it didn't exist. So when you take 72 minus 4 and get 68, basically you're taking this term out. So one option for you is to say 72 minus 4 is indeed 68, but I gotta make sure I add that n equals 4 term back in, giving me a total of 69 terms, which is how many I have. Another way to think about it is if you were to add up 72 terms. So let's say this right here would be the first term, the second term, the third term, the fourth term, the fifth term, 71st term, 72nd term. So you're adding these all up. That would be 72 total numbers you're adding up. If I'm starting at 4, well then I'm only canceling out 3 terms. So how many terms are left? It would be 72 minus 3, 69 total terms that you're adding up. So there's 2 different ways that you can think about this. You can think about subtracting the 72 minus 4, but making sure you add in the other term, or you can just think about how many terms you're actually subtracting out by thinking of it as like a number line. All right, so now that we have figured that out, we have 69 over 2 times the 14 plus the 218, and when I multiply that out, I get 8,004. Good work. All right, so the next example, if a sub k is equal to 8 plus 3 times k minus 1, evaluate the series from k equals 1 to 73 of a sub k. Okay, so it's important here to take a look at my a sub k and recognize that this is arithmetic. Now, it doesn't look like a linear equation in slope-intercept form. It's actually been given to me in that very basic first definition we learned, where my 8 is my a sub 1 and my 3 is my common difference. If I clean this up, you'll see you've got 8 plus 3k minus 3. So a sub k is equal to 3k plus a 5. And then I can see this is an arithmetic sequence, and I can see my common difference is 3 in that slope, but some of you may have recognized that right away. So if I evaluate my series, I'm starting at 1, so that makes this easy. It's 73 over 2 times the first term, which ends up being 8, plus my last term, which, let's see, when I plug in 73, I get a 224. Good, and then when I multiply this out, I get 8,468. There we go. So again, in examples 1 through 3, they're all arithmetic, and that's what allows me to use this logic and this formula. If it's not arithmetic, then I'm kind of stuck with just adding them together at this point. All right, so this last example, I would like you to pause the video and do on your own. When you come back, you'll see all of the answers, and you can check behind yourself, and then if you need to go back and revisit any concept, we can do that. So go ahead and pause the video now. Welcome back. Okay, so you can check your answers now. For number 1, you should have had p sub n equals 2n plus 1. Number 2, when you are asked to evaluate p sub 76, that's the 76th term in the sequence, you should have had 153. Number 3, evaluate s sub 76, that's the sum of the first 76 terms in the sequence, you should have had 5,928. And number 4, evaluate the sum from I equals 1 to 132 of p sub I. So all that does is change my index from I to n, and I am finding the sum of the first 132 terms in that series, and you should have had 17,688. So you guys should be all set now to find sums of arithmetic series, and you can do problem set 4.3 now.